Hello, my name is Marija. I'm a research associate at Imperial College London. I'll be presenting our work, an informative path planning framework for UAV-based terrain monitoring, which was done during my PhD at ETH Zurich. Let's start with some motivation. Why would we want to use robots for sensing? Well, here we see examples of different scenarios where agricultural procedures are done using conventional approaches: static sensors, manual sampling, or piloted aircraft. These methods require large amounts of money and labor, especially for monitoring missions that need flexibility, speed, and involve collecting very detailed data. In such applications, using robots as an alternative presents many benefits in terms of saved time, cost, and labor, while delivering data at high resolutions and much lower risks. To fully exploit their potential, however, several open challenges remain. Consider this UAV monitoring a field shown here in an aerial view. Let's say the field has several areas of interest that need to be inspected more closely, for example, weeds requiring treatment. Following a conventional approach, we create a lawnmower to cover the field at a fixed altitude, given limited battery life. This strategy is simple, fast, and available in most commercial products. However, the major drawback is that the entire environment is mapped with a constant resolution, limited by the pre-planned trajectory. As the distribution of interesting regions is unknown in advance, we can't improve map accuracy in these areas and waste energy on mapping exhaustively instead. Through an informative planning approach, the aim is to perform more efficient, targeted monitoring by allowing the robot to decide where to go next. This way, we can adaptively focus on collecting better data in more interesting areas, leading to a much better use of the limited battery life. Solving this problem presents several difficulties. First, we must decide how to model the environment and define an objective, quantifying the utility of potential measurements. Second, the path should satisfy the UAV dynamics and endurance constraints. Third, a key trade-off lies in the fact that the UAV can see the same point on the field from different altitudes, and we have to account for the fact that sensor certainty degrades with increased altitude and coverage. Moreover, the measurements might be at different resolutions, depending on the altitudes they were registered from. Finally, the algorithm can be made adaptive, so that plans are recomputed as new data arrives. To address this, our contribution is a general informative planning framework suitable for monitoring using an aerial robot. We consider the robot navigating in a 3D space equipped with a downward-facing camera above a flat terrain, as shown. Mathematically, we formulate the informative planning problem as follows. We seek a trajectory for maximum gain in an information measure with respect to the path budget. Here, the function measure obtains a set of discrete measurements from which information can be calculated, and cost gives the associated cost, for example, in terms of time or distance. In the following slides, I'll first present a high-level overview of our approach before going into the details of our methods for environment mapping and informative planning. This diagram shows an overview. On the left, the system takes measurements extracted from a sensing unit, such as a multispectral camera, to create a map of the terrain. The map representation can be either continuous or discrete, depending on the type of data received from the sensor. This map is updated online according to a probabilistic sensor model, as we will see. The map is used to plan trajectories for the robot to follow. The planner objective is to find the most informative trajectories for data gathering in continuous 3D space. A key ingredient here is the utility function, I in our problem formulation, which defines the information measure with respect to the map. This could be, for example, to focus on mapping areas with high vegetation cover. For mapping, in the case of a discrete variable, we represent the area of interest as an occupancy grid. Here we see an example in which the colors represent the probabilities of occupancy of different cells assumed to be independent. Say we receive a set of new classified binary measurements from a UAV pose above the terrain. To update the current map, we use sensor models with altitude-dependent performance. As shown by the curves, for each of the two classes, we consider reducing classification confidence with increasing altitude to capture that trade-off between measurement accuracy and coverage. In practice, this model can be developed in a data-driven manner based on how the sensor behaves at different altitudes. Given these two models, we can then project the camera field of view on the terrain map and apply a binary Bayes filter to update the visible cells. This approach is commonly used for classification and is chosen for its simplicity and efficiency. For mapping continuous variables, on the other hand, the main challenge lies in fusing the dense visual imagery from the camera into a single map in a computationally efficient manner, while accounting for its probabilistic altitude-dependent behavior. Our goal here is to map a continuous scalar field on the terrain. And to achieve this, we use Gaussian process or GP models to encode the spatial correlations in the distribution in a probabilistic way. Essentially, we use a GP model as a prior for Bayesian data fusion as new measurements are received. The approach works as follows. First, we require reference maps to train the hyperparameters of the GP, which can be obtained from previous datasets. Then, given a set of discretized locations in the environment X, we construct a prior map through standard GP regression. This step gives us a covariance maps capturing the correlation and uncertainty at each location in the field. When an image is received, the prior map is updated with a set of new measurements, assuming Gaussian noise. We consider that the visual information degrades with altitude in both noise and resolution. And this plot shows an example sensor model capturing these effects. To account for noise, the variance of each measurement is modeled as increasing exponentially with the UAV altitude, as shown by the curve. To account for resolution, we define altitude envelopes corresponding to different image scales with respect to the initial points. To fuse the new images with the map, the posterior mean and covariance are calculated using a common filter. The fusion step is then repeated recursively as new data are registered. This approach has two main benefits. First, since the map is at a fixed resolution, we get fast, constant time updates, which are important for real-time online applications. Second, as we have seen, the strategy can handle data fusion with variable resolutions and uncertainties. This allows us to use heterogeneous sensors for data acquisition as relevant for terrain monitoring applications. Moving on from mapping to planning, an open challenge here is how to quickly find informative paths in a nonlinear, high-dimensional optimization problem space. To address this, we present a new computationally efficient algorithm suitable for mapping online planning with budget constraints. The approach operates in a finite horizon manner, alternating between replanning and execution until the budget is exhausted. Each new plan is a smooth polynomial trajectory. The replanning involves two steps. First, an initial trajectory is obtained by performing a search over a 3D grid in the workspace. Then, this solution is refined using the covariance matrix adaptation evolution strategy and evolutionary optimizer. To evaluate trajectories, we calculate the information gain along it, defining the objective based on the current environment model. This approach has several desirable properties. First, using smooth trajectories, we obtain dynamic feasibility. Second, a key feature is the use of the discrete grid search to initialize the optimizer. This enables us to converge much faster to a good solution than by using naive initialization, as commonly done. Finally, by using fixed horizon planning, we can create adaptive plans to map areas of interest online as they are discovered. Moving on to the results, our framework was evaluated extensively in simulation. With the robot starting in an unknown environment, we compared our approach against the rapidly information gathering tree, a state-of-the-art informative planner, lawnmower coverage pattern, a spiral coverage pattern, and random motion. These plots show how different informative metrics evolve during a mission in terms of uncertainty and error. Looking at the red curve, the fastest reductions in uncertainty and error confirm that our method performs best. And this is because it allows the UAV to collect low-resolution images before descending to refine the map. To demonstrate system integration, the approach was applied to map a publicly available dataset called RIT18. We considered 3 different classes in the dataset for mapping and defined the class of man-made features shown in green as being interesting for a targeted exploration case where online adaptive replanning is necessary. In the experiments, we compared targeted and non-targeted variants of our approach against 2 complete coverage patterns. These plots show how map uncertainty and error evolve over time. There are 2 key points to take away. First, as before, our approach reduces uncertainty much faster than coverage. Second, we showed that our planner can adaptively focus on interesting areas to improve mapping much quicker in these targets. This general property is very relevant for any scenario where a particular class on the terrain needs to be found. Finally, the complete system was deployed in an agricultural monitoring scenario with outdoor vision-based state estimation. And the aim here was to map the excess green level index on the field from the camera images. Here is a short video of the experiments. We can see the UAV moving around to explore the space and stopping briefly to replan. These plots show how the field map evolves as measurements are collected. The color map signifies the levels of excess green index, with the yellower shades corresponding to areas of higher vegetation. As expected, we can see the map becoming more complete over time. And in particular, we can see that the UAV successfully detects the less green soil and crop region in the center of the field and the greener weed regions towards its edges. In conclusion, we introduce a general informative planning framework for environmental monitoring using a UAV. The method can map either discrete or continuous variables on terrain using variable resolution data received from probabilistic sensors. The resulting maps are used for planning by optimizing continuous space trajectories. The key features of the planner is that it can quickly converge on good informative paths in a high-dimensional workspace on systems with limited computing power, and its online nature allows for its use in adaptive planning scenarios. The system was evaluated in simulation and demonstrated running on physical platforms with real-time requirements. Finally, we release our framework open source for you to run on your robots. We hope that this will encourage future work in using intelligent robots on the farm. Thank you for your attention.